All right. So I want to hear from. Let's hear from Garrett. Okay, that was interesting. Thank you, Garrett. Let's hear from Sky. Go ahead. Read number 1, please. Try to speak loud, okay? Appreciate it if everyone else is quiet. A little bit louder, one more time.
Where on the track is the skater when the energy is lowest?
What you think, homie?
At the top.
At what?
At the top of each player.
Is you what you were saying? You agree or not?
Yes,
Oh,
I
that's
agree.
okay. What do you think?
I agree.
At what moment, where is the skater when the kinetic energy is low? What do you think? Huh? So it's highest height? Does everyone agree with that? Everyone's good? Good job, dude. Nice. Next problem, please. So kinetic energy, you say, is lowest when the skater's at the highest spot. Okay. I want to hear now from Ashley. Go ahead, number 2.
Describe the skater's velocity when the skater's kinetic energy is the highest. Describe the skater's velocity when the skater's kinetic energy is the lowest.
Okay, what do you think? Do you guys agree with that? One more time for homies.
Velocity is at its maximum when kinetic energy is the highest. When velocity is the highest. When kinetic energy is the highest, velocity is at its maximum.
Do you guys agree with that? Now, let me help you a little bit. If we imagine a velocity vector for this guy, right? Is the velocity vector staying in the same direction? Is the velocity vector changing direction? Do you guys see how the skater changes the direction he's moving? So I want to simplify your life. Do we have to worry about the direction he's moving when we talk about energy? In other words, is energy a vector? So it's not a vector, it's a scalar, right? So instead of thinking of it in terms of velocity, how can we think of it? In terms of its velocity without direction. So say what you said, but replace the word velocity with speed and it'll be perfect. Is everybody good there? Yeah? You guys like it? I thought that was beautiful. Thank you, Ashley. Good work. Richard, go. Yeah.
Does kinetic energy depend on velocity? If so, how? If not, what does it depend on? I think it does. Does it depend on? I think it does.
Replace the word velocity with what?
Speed.
Why? Are we concerned with the direction this spool is moving? You guys cool? Again, we're trying to simplify your life here. You guys good? Nice work. I think we're good with that one. Andrew, next, go.
Where on the track of the skater when the gravitational potential energy is the highest? Where is he when it is the lowest?
What do you think?
Probably the highest when he's at the as far as he can go, not at the top.
So tell me when to pause it. You want gravitational energy highest or lowest?
Highest.
Okay, tell me when to pause. You guys agree? I can prove it to you. You did good, my boy. Look. Is he right? And it's nice. Did you guys put this bar graphs on and check it out? I hope you did. Watch now. We can even slow down time. I wish I could do this in real life. It'd be so fun. I would love that. Today is Old Man Night at Skate Lab in Simi Valley. You guys know about that place? Maybe I'll have to go there. It's like $5 off or something. There's a bunch of old bald fat guys like me skateboarding. Lots of fun. No, there's good ramps there. Wood. There's a nice wooden bowl. It's like a giant pool made out of wood. So cool. Cool. Are we good with that one? You guys all good with that one? No questions? You're cool there? There's some stuff I wanted to show you, but I will wait. We'll wait till they come naturally. Tiara, go. Try to speak up, I'm chicken.
Describe the skater's velocity when the skater's gravitational potential energy is the highest. Describe the skater's velocity when the skater's gravitational potential energy is the lowest.
Okay, we want highest or we want, what was the first question? I got really confused there.
Describe the skater's velocity when the skater's gravitational potential energy is the highest.
Okay, when is the gravitational potential energy the highest? Tell me when to pause it, please. Tell me when to press pause. Okay, good. Can we replace the word velocity with speed to make it simpler? What's the speed at that moment? Maximum or minimum? Watch it. Watch again. We'll do it on the other side too. Except I won't pause it. When the gravitational potential energy is maximum, right? Now it's coming, right? What do you notice about its speed? So we could say that when the gravitational potential energy is maximum, what's the speed? Everybody? So if the speed is 0, what's the energy stored in the motion? Do you see what's going on? The energy is doing what? It's transferring from where to where? A little louder, please. So good. We're going from blocks that are stored in the gravitational field bin, right? And those blocks are being moved to the kinetic energy bin, and it's moving really fast. Now, did we lose any of the blocks? So none of the blocks were lost. What's your evidence? Look at this last bar graph here. What is constant? So you add these two. What storage bin is not included on this simulation? Do we need elastic here? Is there a rubber band, a spring, a trampoline, a bungee cord? Is there anything like that? So we don't need an elastic bin. Thermal bin we'll talk about a little bit later. Not yet. And we call it something else. Okay? You guys good though? Why is it that we're not losing any blocks out the window? What are we ignoring here? Air resistance. What else? Friction. What else? Any other ideas? If I spun a skateboard wheel in real life, would it eventually slow down? This is a magic skateboard. It doesn't. It has special bearings in it that never slow down. That's the only way this is possible. So we are ignoring friction, air resistance, things like that. Are you guys good? Excellent. Next question, please. I'd like to hear from, by the way, nice work, Tiara. Dennis.
Does the skier stop at the same height on the opposite side of the track?
Yes. Why? How do you know? What are we ignoring? So if there were a bin for the energy that's going to friction, air resistance, heating, that's called thermal because it's all heat, okay? If there were energy going here, what would the skater do? Eventually slow down and stop, yeah. But he's going to the same height because we're ignoring that. Everybody cool? Good work, Dennis. Paulina. I don't know what, it's class dojo, it's not me. I don't know how it knows to do that. I call that magic. Can't hear your nice voice. I'm sorry. Okay, so thank you, Paulina. You're awesome. So we want one side, boy, that was a nice little, we want one side to be steep. Is that what it says? So one side steep, and here, I'll just put this one over here. Boy, that looks nice. I'm doing a good job, huh? I'm having fun. That's important. Okay, I'll make this one gentle slope up. I'll make it, oh, that's like so not, okay, there. It's getting better. It's getting better. Does that look pretty good? It's getting better. This side's steep, this side's not, and I'll have them both sides go to about 8, and I'll start homing right here. Is this what they wanted? Now, I ask you, is the skater going to go to the same height on the other side? What do you think? Is he going to end up at the same height over here? What do you think? Same height, yes or no? Why? In fact, I'll just tell you the official name. We have a catch-all phrase for air resistance, heat, friction. It's all heat. It's energy that goes to little molecules. When you rub your hands together, are you guys with me? You rub your hands together, you feel heat because molecules speed up. Friction, if you think about it, is heat. Air resistance, if you think about it, is actually heat. Because something flying through the air hits molecules that end up speeding up due to that. Does that make sense? So, in the friction inside the wheels, heat. So, we have a catch-all phrase for energy going to small molecules moving. And that's this category, thermal. We call it energy dissipated. So thermal, energy dissipated, they're sort of like the same thing. You guys good? We're ignoring that. So of course skater's gonna go the same height. Done deal. Cool? Very good, Paulina, thank you. King, go. Yeah. Go ahead. Okay. So what's kinetic in your own simple, beautiful words, please? What does this energy bin mean? Energy stored. You guys can help the man. I'll give you a hint. K-I-N-E is Latin for what? What? Motion. So what's this bin all about? What's that energy stored in motion? Yeah. What's the gravitational potential bin? What's that all about? A little help out there, please. I should probably help you with this one. When is this the biggest? When is gravitational potential energy the biggest? When something's higher? Okay. When, if I hold this above my head, when is it the scariest? Does it need to be lifted for it to be scarier? So there's more energy stored in the gravity field. Why do we say it's in the gravity field? Would this energy be stored if I moved my location so that I was not in a gravity field. Please look here. Okay, it didn't change yet. Hold on. Give it a minute. There. What happened to gravitational potential energy? Now, this is just an idea, okay? Is there anywhere in the universe you can think of where the gravity field strength would be 0? It would be the opposite. It would be like a giant infinite number. Make sense? So, is there anywhere in the universe where you're so far from anything that this will really be 0? So this is, go ahead.
The space frequencies.
That we know of, is there a place that exists where the gravity field would be 0? As far as we can see, this can't be exactly 0 because you go infinitely far from things, then you've got this as 0. But how are you going to get infinitely far from everything? It's an idea. So this you can only do with the simulation. You guys with me? So we can change the gravity field here. So that was Earth, around there. And then we could go to Jupiter. What's going to happen to the gravitational potential now? Gravitational potential energy now. It hasn't adjusted yet, but it will. Should it be bigger or smaller now? Let's see. It should be like off the page if I'm right. Yeah. So I have to actually scale this thing now so that I can see it because it's so big. You guys get the idea? So what is this? It's energy stored where? In a gravity field. Do you need a gravity field for this to be scared? Yeah. So the only way you're storing energy in a gravity field is if there is a gravity field. There's a planet, sun, moon, whatever. Now, when you leave the Earth's atmosphere, does the gravity field disappear? If the gravity field disappeared, which many people actually believe, then would the moon orbit the Earth? Where the moon is orbiting, the moon actually accelerates towards the Earth. You guys with me? In other words, the moon is falling about, I think it's a 20th of an inch every second. If you're on Earth, you're falling 16 meters every second. No, 16 feet, my bad. 16 feet in a second. You guys with me? If you throw something horizontally fast enough, you can fall at the same rate such that you stay in orbit because the Earth is curved. Make sense? Now, if you're in the moon's orbit, you can do the same thing, right? But you're falling a smaller amount each second. You guys good? Let me ask you one thing really quick. Does your mass, is everybody with me? Does your mass affect your acceleration due to gravity? Can I hear something from everybody now? Does your mass affect your acceleration due to gravity? So if we put a P, very small mass, where the moon's orbit is, how much will it fall each second? Not 10 meters per second squared. That's only on the surface of the Earth. That's the gravity field here. But where the moon is, there's less gravity field, and it's going to fall like a 20th of an inch every second. You guys getting the idea? The gravity field strength depends on where you are. You guys get it? Does your mass affect your gravity field? Does your mass affect the acceleration due to gravity? Does your mass affect your gravity field? The gravity field, George, is the reason for the acceleration due to gravity. Let me see if you get it. So, since the gravity field is your reason for the acceleration due to gravity, the gravity field is 10 newtons per kilogram here. What's the acceleration due to gravity here where we're at? Earth's surface. How about everybody? What's the gravity field strength here? What's the acceleration due to gravity here? Where the moon is, the acceleration due to gravity is 0.03 meters per second squared. What's the gravity field where the moon is? 0.03 newtons per kilogram. Do you see how it works? Does your mass affect the gravity field? Does this skater's mass affect, if we move him to Jupiter, like he is now, is this gravity field affected by this guy's mass?
Yes.
So we could put any mass in this gravity field and it would behave the same way. It would have the same acceleration. Are you starting to get it a little bit? Now, here's the crazy part with what you're learning. When we talk about energy, stored in a gravity field, did you guys play with this line? Okay, I need 100% right now because this drives people crazy. But I think it'll make a ton of problems in physics a lot easier. Do you see this dotted line I just put in here by clicking the button? Okay, let me put the bar graph back. So watch the blue. Watch the energy stored in the gravity field when I move the blue line. Tell me where the simplest place to put this line is. Because in every problem you get to choose. Most people think it belongs here. It doesn't. Where's the simplest place to put it? Notice this graph, that's your hint. At where? So what level? You guys yell when it's at the level you want. Huh? Here? Okay. Why'd you choose there? So whatever, in any physics problem, let's say I take my cup, I slide it across the desk. Was there a change in height here? No change in height. Essentially, does gravitational potential energy change? So if we call it 0 or 1,000,000, it's the same in the beginning as it is in the end. Am I right? We don't even care about it. It cancels out of our equation. The beginning and the end are the same number. Are you guys good? When there's a change in height, if we choose the lowest height, then at least there's one moment in time when the gravitational potential energy is what? Don't you want one term in your equation to be 0 so that you don't have to worry about it? If you leave this down here, you got an extra thing to calculate that isn't helping you. So, are we saying there's no gravity field there? Are we saying there's no force due to gravity? Are we saying there's no acceleration due to gravity? Don't confuse those. We are simply saying that's our reference line where the energy stored in the gravity field is 0. You guys good? Cool? Again, are we saying there ain't no gravity field there? Nowhere in the universe there's no gravity field. Cool bananas? Excellent. So that's a confusing part for many students. Hopefully that helps you. What question are we on, Tristan? Go ahead and read. Okay. So we slowly move this guy up and down. What's happening? Help. Just Tristan, please. You guys good? I thought that was beautiful. Anyone need it repeated? Now it's the higher he is, please don't miss this subtlety. It's the higher he is relative to where? Relative to where? And who chooses relative to where? Is it relative to here? Who chooses this dotted line? You do, right? So it's relative to where you choose. Height relative to where you choose. That's just a slight modification. You guys good? Beautiful, dude. Good job, Tristan. Joanna, go. Okay, what do you think's gonna happen if I select, I don't know, you get to choose, man. Here, I'll move the bar graph over here. Tell me which skater you like.
That one.
It's Joanna's choice. Huh? Everybody today choose the dog. Everybody likes the bulldog. What happens?
There's a ball.
Here, I'll just see the pattern in what happens here. As I choose a different skater, what's the mass doing? A little louder, please. That was beautiful. Since you guys couldn't hear anything, I will repeat what you say when you say it. What? Say it slowly so I can say it. Huh? The mass. So the mass is changing, and what's happening to the gravitational potential energy? What's happening to the energy stored in the gravity? More mass? More mass? What? So more mass, more energy stored in the gravity field. Hey, if you're standing under a big bucket of hot tea, and all of a sudden the bucket has more mass, scarier? So mass is important. You guys good? So there's more energy when the mass is bigger. Yeah. Beautiful. Yeah, you actually, thank you, Joanna. You actually have a good sense of energy just from your daily experience. You already know when there's a lot of energy stored somewhere because it's dangerous, right? You've learned that. Let's try Austin. Next one, please.
Reset the skater and see the 7-speed slow.
Okay.
Turn on potential energy reference.
Oh, this is what we just did, yeah? So turn on this one, this line. Okay, go ahead.
What happens to the bar graph? Move the bottom line up when the skater is at its highest point.
So you move this, up here? Tell us what happens. Well, there's less total, that's right. Why? There's less energy stored where? When we move this up, there's less energy stored where? So all we're changing is the gravitational potential energy reference line, right? This is our 0 for gravitational potential energy. How about now? What do you guys notice? As I move this down, what grows? And what also grows? Do you guys see the blue graph? I should pause it so it doesn't get too confusing here. So, do you guys see how this line directly should influence the blue graph? It should. I guess I got to push play for it to do that, but do you see how this line directly influences the blue graph? Higher this line, the more negative. And the less total. Well, this isn't force. What is this? Okay, good. So it's the sum of these two. And we're ignoring dissipating energy, so we're ignoring thermal. Is everybody good with this one? So the higher you up, the further higher you are relative to this blue line, the more energy will be stored in your gravity field, right? Good work. Jason, go. What happens if what? Okay. So move the track down. What happens? Is there any difference between moving the track down or moving this up? It's all the same. You guys cool? Sebastian, go ahead. Okay, we did this. We'll do it again though. I'll put the skater at his low point, and we be moving to Jupiter. Actually, I think we're already on Jupiter, so I'll move. That was fine. Move to Earth. What happened? What should happen with the bar graph before I show you? If I move to Jupiter, if I move from Jupiter to Earth, the gravity field went from 30 to 9. What's going on then? Joe Sebastian, please. The amount of energy stored where? Are you guys good with that? Good work. You guys are going to do fine. Michael, next one, please.
You said scalar. What happens to change location of fluid? Scalar is at its lowest point and its highest point.
So what do you think? Just tell us what's going to happen. I think you guys should know it by now. How does gravitational potential energy change? Complete sentence would be good here. Go ahead. You guys good? One more time for those that missed it because they were talking. Everyone good? Beautiful. Thank you, Bergman. Michelle, next one, please. I can't hear you. Sorry. What do you think, home chicken? Gravitational potential energy depends on what? Speed?
Yes.
Careful. Look, I'll prove it to you. Is this guy moving right now? Okay. I'll put my bar graph up. How can I change the blue? I don't know why I can't get anything back.
It's on the side.
Oh, it's on the side? Okay. Oh well. Bar graph. How do I change this blue?
You take the
Does the speed matter, first of all? I mean, I could literally take the skater off the ramp, put him back on. He ain't moving. Pretend he ain't moving. There isn't a significant change in kinetic right now, right? So he's not really moving. He's moving a little. Let's forget that. How can I change this? Give me 2 ways.
location.
Good. There's that 3 ways. Change his location so I can lift him up. Everybody good? So that's his location within this gravity field. This 10 Newton kilogram gravity field. This 10 meter per second squared gravity field. You guys good? There's 2 ways. That's one way. What else can I do? Yeah? Yeah, I can. You can give me 4 ways. I could change where our reference line is. Beautiful. Give me 2 more ways to change the energy stored in the gravity field. Okay, so I can change the actual gravity field itself, right? Give me 1 more. The energy stored in the gravity field, there's 1 more way. What if I change this guy to the dog? You guys cool? So if his mass changes, the energy stored in the gravity field changes. Any of these changes, once you're in a gravity field, once you're in a specific location, can you change that gravity field? Once you're in a specific location, does that gravity field change? So it's constant once you're in a specific location. Hey, let me show you your homework, and then I'll let you go in a minute. Which problems didn't we do? 14 14, 15, 16, where you design stuff. How many people you tried that already? Okay, so for the rest of you that didn't try it, I really want you to try it because designing things is fun and good for your brain. So, I want you to finish this worksheet, do 14, 15, 16. All right? Let me take you to your website real quick. Appreciate it if you all look here. Appreciate it if there's no noise. So, finish 14, 15, 16, and then on your website, there's a worksheet that looks like this. I can't get it, sorry. This one, it's called Where is Energy Stored? All right? I want you to do this worksheet. You know the other worksheet that had 3 problems that Guzman did by accident? I posted 3 videos. Problem 1, problem 2, problem 3. Those problems are harder than this worksheet. So I want you to watch those videos to try to understand and attack this worksheet. Do half of it. Does that make sense? So finish Energy Skate Park Lab. Do half of this and watch the videos for support to figure stuff out. Does this make sense? Cool? So that'll be 3 points tomorrow. Sound reasonable? The key to you getting it for the next celebration is you actually succeeding at problems like these. Okay? So you're going to get half of this done tonight. Have a good day.